Thanks for inviting me. I'm very honored to be here. I just want to warn you, there will be no spikes, no equations. This is more high-level modeling. So I want to start by talking about CNNs, and they encode several priors. So this is my daughter Tess and my dead dog Wally. This is my live dog, Casey. And they encode several different properties of the visual world. So for example, nearby pixels correlate the most with nearby pixels, not pixels far away. And so that's a kind of locality of the data. On the other hand, if you take all your vacation photos, say, and you look at the statistics of a pixel right here and the statistics of a pixel over here, they will have very similar statistics. Of course, that's not a correct assumption necessarily, because the sky is usually blue and the ground is usually green or brown. And the identity of an object doesn't depend on its location in the image. So this would be Tess here if she was here, or if she was over here in the image. So there's translation invariance in that sense. And objects are made of parts. So Tess has hands, arms, a body, and a head. So convolutional neural networks encode these. And this began with Jan LeCun's famous papers in 1989, but I would like to call out that actually there were a convolutional neural network in chapter 8 of the PDP book under the name of the TC problem, and they reference Fukushima even earlier in 1980, as does Jan. So they have small local receptive fields, as you can see down here, and learned features, so that encodes the locality. Those are replicated across the image to give reflecting stationary statistics, but maybe a better way to think about that is if a feature is useful in one place, it's useful in others. And spatial pooling combined with this convolution gives you some translation invariance. And objects are made of parts, so receptive fields earlier in the network will encode smaller features, where ones later in the network may encode the whole object. So one thing that isn't considered here is the resolution of the image. So CNNs have high resolution everywhere. And with translation invariance, that's good for recognizing objects in any location in the image, but let's try this on Zoom. So I want you to fixate this cross over here. Don't move your eyes at all. And you can unmute yourselves while you're fixating this. And now tell me what the word is over on the other side.
And? Nope.
Yeah, kind of hard to do, right? So much for high resolution plus translation invariance. We only have high resolution in the fovea, which is about the width of your thumbnail at arm's length, while CNNs have high resolution everywhere. So I'm going to incorporate some of those considerations in the model 2.0, but first I want to briefly mention the model. I developed this over the last few years. Tommy Poggio had the standard model at MIT, so I decided to call mine the model. And it starts with a convolution by multi-scale Gabor filters. Hey, it's convolutional. And then does a form of statistical pooling with PCA. Hey, it does pooling. And then these hidden layers here learn features in the service of the task. So you could have one that's good at recognizing faces, and then the hidden layer encodes the features of a model fusiform face area, or it could be just a basic level categorizer, and then this encodes features in lateral occipital cortex. So it's deep, and so it's a deep convolutional neural network, and it develops representations, which are now called image computable representations. And so the approach I use, I trained the model to do the same tasks that people do, like recognize faces, emotions, objects, and letters, and that's now called task-driven vision. And then I use the model to explain various behavioral, developmental, and neuroimaging results without any fitting parameters. One example of what I did with this is explain, if you believe the expertise hypothesis, that the fusiform face area is recruited for other expertise tasks. So if you become a birder and you spend your weekends looking at birds, the fusiform face area ends up lighting up for birds. And I have a paper where we claim that we can explain why that is. So with this model, I accounted for a lot of data. It's been 30 years, so there's a lot of data. That was the model. And now the model 2.0 is more anatomically inspired. So this was anatomically inspired in the sense that for Gabor filtering, that's a model of early visual cortex. PCA captures some of the global structures here. It might, if you're doing faces, it might encode the occipital face area, etc. And so the new model, the model 2.0, it's deeper, has more anatomical constraints. So it has a foveated retina, the log polar mapping from the visual field to V1, central and peripheral pathways, and sampling of the image using salience. So in this talk, I'm going to talk about two results with this model, the simulation of some behavioral data by Les Loschke and Larson, and the face inversion effect. So here's the first anatomical constraint. So in your fovea, in the about 1 degree of visual angle, you've got a huge number of, it's packed solid with cones, and then the cones drop off radically outside of the fovea, and we get a lot of rods at that point. And the number of rods goes down linearly here with, or the density goes down linearly with eccentricity. So because we can only see high resolution at the size of about a thumbnail at arm's length, we move our eyes a lot. In fact, we move them about 3 times a second. So if you pencil that out for 16 hours a day, that comes out to 172,000 times a day. So this is the one decision we make more than any other in our lives, is where to look next. It's not as important as who to marry, but it's much more frequent decision, except maybe for Donald Trump. And then from the retina to V1, there's a log polar transform. And what that does is you end up with all the foveated data taking up almost half of the V1, and then the peripheral data, the peripheral input drops off logarithmically as you go farther out in eccentricity. So you get this huge cortical magnification. Now, it's not really magnification, it's just because you have so many inputs coming from here, it has to go somewhere, and that takes up a large fraction of V1. So the mapping from the visual field is approximately log polar. So that's the logarithmic log of the radius, how far out, and then which way theta, so it's log r theta. So as you can see, this drops off logarithmically this way, and then the theta part goes from 90 degrees up to 270 degrees. So that's one visual field. And that, notice that this separates the central representations from the peripheral ones. And that makes it possible to have two pathways coming from here. So this is from data from Colonnette Grill Spectre. The red here is central vision and the green is peripheral vision, and this innervates the FFA and places like that. And this one will innervate the parahippocampal place area. So now the map is formatted for these two pathways. Here's a central and peripheral, and this is what an original image looks like. This is what it looks like if we foveate that. And this is what it looks like if we log polarize it. And so this is modeling that. It's not oval, but it's close enough for government work. So here's a version of the model with these two pathways. There's a central pathway and a peripheral pathway, and these are just two identical networks that are then trained using a mixture of experts architecture. So again, it starts with a foveated retina. We've got the log polar representation, and then two pathways from V1, central and peripheral. And these two pathways compete using this gating network to solve tasks. So for what comes next, we're going to use three models here. I'm going to give some results of this model. We're going to use AlexNet here, or VGD, or GoogleNet, which is pronounced GoogleNet, not GoogleNet, in honor of Jan LeCun. And then we're going to fine tune them so they're pre-trained on ImageNet, so they're not used to this representation. So we have to fine tune them on foveated images. That's the model 1.9. And then also fine tune them on log polarized images, and that's the model 2.0. And then we're going to train them on versions of a scene classification data set. So how does this model account for the Larson and Loschke data? Well, what is the data? This is an experiment they did with human subjects where they gave them a version of tunnel vision in these four conditions, or a version of having a scotoma in these four conditions. And the job of the subjects was they had 10 different scene categories, and they were given a label like forest, and then they had to say yes or no, is this a forest or not? And I don't know if we would call this a forest or not, but we're using the same stimuli for our network, using the same stimuli type. And again, it's just a binary decision. So chance here is 50%. So my student originally just did a foveated version. This was for, I think, a special issue. And I call that the model 1.9. And then there's a log polarized version. One thing to notice here is how much of this is peripheral vision compared to Euclidean coordinates. So this is what the human data looks like. So for the blue line here corresponds to these four conditions. And you can see with this, you're down practically a chance. And for the red line, you can tell what it is for a long time, and even pretty well, even in this situation, way above chance. So this is the model 1.9, the foveated version. I kept telling Panchu, use the log polar, use the log polar. And he said, oh, this is fine. It does a crossover here. That's all we need. And then the reviewer said, what about cortical magnification? I said, yes. So then he had to do the log polar, which I was very happy about. And in this case, it turns out that VGGNet adapts to the log polar representation better than the other two. So I like to look at these curves, the top ones here, and notice the difference between this representation and this one. This stays high for a long time, whereas this one drops like a stone. And so the crossover point here, it's doing much worse than the humans. But when you log polarize it, it maintains its ability to recognize what kind of scene it is much longer and drops off much more slowly. So the model explains the data better when it's more anatomically correct. And so you can explain these results. That's what I like to do with models, is use them to explain results. Notice that this is all the information. So think about the red line that's in this situation. Is the 1 point, this is just foveated. Here's log polarized. And notice that this is the only input in our model that the peripheral pathway got. And notice how much longer that input is preserved here compared to this. So it's doing much, it's getting a lot more of the information it's used to, and that makes it able to maintain its representation or maintain its accuracy much longer. Similarly, with the blue line, you get a lot more central information than you do here. You know, at this point, you're able to tell you're getting some of the peripheral information. And as the peripheral information increases, you're able to recognize what it is much better. So I know we're not supposed to interrupt. I really didn't like it when David imposed that new that new thing, because I love to ask questions in the middle. If anybody has any questions at this point, I'd be happy to take some before I go on. Any questions? Let's go on. So what are some good things about this representation? First of all, it's biologically plausible if you care about such things, and I do. It's still retinatopic, and so standard convolutional networks can process it. And it's scale and rotation equivariant. Both of those are just a translation in this representation. So here's Jeff Hinton at multiple scales, and this is the XY coordinate or Euclidean coordinates, but here he is in log polarized coordinates. So it's just the same representation, it's just shifted to the right. Okay, and so it's going to be scale equivariant at the first layer of the convolutional neural network taking this input. And I find the hoops that computer vision people jump through in order to achieve this kind of scale invariance to be rather baroque. I had one student of Poggio's at VSS a few years ago. He had 3 networks, a big one, a medium-sized one, and a little one. And that just seemed crazy to me. And then rotation is just a shift up and down. So here's Elon, and Elon tilted. I guess he's a little stoned here. And when these are fed into a standard connet, which is mostly translation invariant. So again, this is just a shift up and down. Notice his nose here just moves up a bit. And when you feed this into a standard convolutional neural network, which does translation invariant from that point on, you get rotation and scale invariance. But now translation invariance in the original image is lost. And so this is the kind of augmentation you get for a standard convolutional neural network, which I find kind of crazy because, I mean, you're giving more input to a neural network that's already translation invariant by translating it. Of course, there's other augmentations that are used, but here's the same image, and here it's focusing on the mouth, I think this between her forehead, this is one eye, this is the other eye, and this is her nose. And so these are, we make up for losing translation invariance by training the network on images at different fixation points on the image. And so it has to learn that these 5 inputs all represent the same person, which should be, I would think, is a much harder job actually than knowing that these are the same person. So the one thing I really like about this is it means that when we're looking around doing our 172,000 fixations a day, we're actually performing self-augmentation of the data. So all of these are different variations of the same image, just different fixations on it. And one of the things that obviously we do is, it's obvious we learn to talk, but we also learn to see. And so one of the things we're pursuing at the moment is looking at self-supervised learning with this kind of representation. So, okay, so how does this model account for the face inversion effect? So this was first studied by Kohler, one of the Gestalt psychologists, early Gestalt psychologists, and he noticed that faces appear strange when they're inverted. And so he devised a clever experiment. As a Gestalt psychologist, he wanted to know whether this was because of the relationship of the environment, the face to the environment, or was it due to the projection on the retina. So he did the following experiment. He bent over and looked through his legs, and that's Kohler's face there, pasted into this. And he had an assistant hold up a picture of a face right side up while he looked at it through his legs. And it still looked strange. But when the assistant inverted the face, it looked normal. So his conclusion from that was that it's the projection on the retina, not the relationship to the surrounding environment. So there's been some other work since. So one of the ones that is a touchstone for us is Yin's experiment in 1969, where he did recognition experiments with faces, houses, and airplanes. And he found that when faces were inverted, people's performance dropped off radically compared to when objects were inverted. And in between those two were mono-oriented objects, houses, which we, like faces, we have experience mainly with them and right side up. And then another touchstone is Diamond and Carey's experiment that said it's an expertise effect. So dog show judges, they showed that dog show judges were similarly disrupted by inverted pictures of dogs. And in one of their experiments anyway, non-experts actually performed better than dog show judges on inverted pictures of dogs. So that says this is an expertise effect. We aren't house experts, or most of us aren't, unless you're a real estate agent or an architect. But faces are a homogeneous category. We all look alike. We have 2 eyes, a nose, a mouth, and 2 ears, and yet we have to individuate each other if we want to be socially acceptable. And then Farah and Tanaka said it's due to holistic processing. And by holistic, I don't mean some California thing with incense and crystals. I mean, configural information. So the relationship of the eyes to the nose and the eyes to the mouth, etc., the configuration of the features. And then Yovel and Canwisher said this happens in the FFA. That's where the effect arises, not earlier. But I wonder whether it could start in V1 due to this log polar representation. So again, face recognition is an example of visual expertise. So this is actually the same woman but they look different. And that's because in this image, her eyes have just been shifted up. So we're going to do another audience participation. You don't have to stop the recording, I think, but please unmute your microphone and tell me which of these two images I'm going to show you is the real George W. Bush. Okay, ready, set, go. Left or right?
Right.
Right.
Okay, all right, you say right. Let's try again, right side up.
Oh, God.
Left.
Okay, the people that were brave enough to speak actually were correct both times. So here I've used a feature of PowerPoint which allows you to cut out an oval, and I've shifted his eyes up a bit. So the arrangement of the features is critical, and you disproved my hypothesis that you would be worse at upside down ones. How about this? Who is this?
No.
Adele, yeah. But she's had her features inverted in this image, so when she's right side up, it looks very strange. Okay, so that's an example of how configural information is important, and we're much worse at upside down faces. So how am I going to explain an inversion effect when the model is rotation invariant? It seems like it should be impossible, right? Well, the answer is that there's a topological difference between rotation and scale in the log polar plane. So rotation is a circle group, right? So, and your brain is not a torus. So your cortex is not shaped like a Coke can. So the shift due to rotation, when it goes up and down, actually falls off one side and reappears at the bottom. So here's an example. As you know, everything on the right side of visual space goes to the left hemisphere. So this is the polar coordinate of this point, and and the coordinates go around down to here. So you've got 270 up here and 90 degrees down here. So when an input rotates, it falls off the top and appears again on the other side. And that rearranges the features, and configuration matters in face recognition. So again, as you can see, this is just a shift up and down. But if you look at the first one, the nose here in the input is next to the left eye. A small rotation, the nose is still next to the left eye. But when it's completely inverted, now the nose is next to the other eye. So we've rearranged the features and we've disrupted configuration. And if this is an expert category, where like faces are for most of us, then we've disrupted the configuration of the features. And another thing to notice here is that the features themselves are still identical. So all of these noses are the same. All of these eyes are the same. So they're just shifted up and down. So it's a common story told by psychologists that when we invert a face, we resort to feature processing only. And in this case, in this representation, the features are preserved. And if we feed these into a translation invariant network, we're going to recognize these features no matter where they are in the image. So we're reduced to just features at that point. So we used a simplified version of the model for this. So we have a foveated retina and the log polar mapping, but we didn't have two pathways. So we call this LPNet. And we used ResNet 50 here as our base thing, and we trained it from scratch. So we trained it on face recognition. But one thing to notice that we did is that in order to model how we develop face recognition capabilities, at first, we mainly see our parents. So we started with two or four different faces, and then incrementally doubled the number of faces. So first, you know, your parents, your siblings, then you go to preschool, you learn some more faces, then you go to grammar school, you learn some more, etc. And then we tested it on upright and inverted held out faces. So obviously, in order to compare, we trained a vanilla CNN on the same data. So this is what we get. One thing about this is that the variance on faces was very high, and we're not sure why that is. This is the only place where this happens. But initially, when trained on 4 faces, the orange line here is the holdout set of the same 4 faces, but different images. And the red is the inverted version of the holdout set. So we get we lose some, we get a very small inversion effect at first. But as we learn more and more faces, so then 8, then 16, then 32, 64, and 128, the inversion effect gets bigger and bigger. And the same thing happens with the CNN. The inversion effect gets bigger as we train it on more faces. So what? I mean, they're both showing the same kind of effect. Well, the difference is that the CNN drops to nearly chance. They can't handle inversion if they're not trained on inverted faces. So this doesn't model what humans do. We aren't at chance suddenly. You knew that was Adele, even though she was inverted. Whereas the CNN would not recognize that as Adele. And it's much less. So what about, so that's expertise, right? We're all face experts. This network is a face expert. What if we train it on object categorization? Then the inversion effect is much less severe. And that's, you know, the story is that we don't care about the configuration, you know, not as much anyway, for objects. We still take a hit, but the hit is much smaller for inverted objects. Okay, so this suggests the network doesn't care so much about the configuration of the features, just the features themselves. And again, that's what we claim. You know, psychologists claim that when you invert an object, you're stuck with object processing. This is a network that does object level processing, just categorization of 128 different object categories from ImageNet that were not mono-oriented. So these are objects like screwdrivers, things like that, that the orientation doesn't matter. But so what about Diamond and Carey? So Diamond and Carey showed the same effect with dog show judges. So we used the 117 different dog breeds in ImageNet. ImageNet is a very strange data set. Any network trained on ImageNet becomes dog expert because there are 117 different dog breeds that they comprise about 12% of the categories in ImageNet out of the 1,000. And notice that LPNet again shows a bigger, the inversion effect gets bigger the more dog breeds it learns. And the CNN again is much worse than these are significant differences. You don't need statistics to see that. So overall, our networks match Ian's 1969 result. We also, among the objects that we trained it on, we added in houses, and we saw that in our model. I'm not showing you the data right now, but the size of the inversion effect is biggest for faces, intermediate for houses, and least for objects. And that was what he found in his data in 1969. So, and similarly, we matched Diamond and Carey's result that dog show judges show an inversion effect. So we also did this with cars. The same thing is true of car expertise. So there's nothing special about faces per se. It's what we do with them. And, you know, there are a lot of papers out there with titles like Faces are Special, or Are Faces Special? Why are faces special? Faces aren't special. It's that we have to individuate them at the subordinate level, that which results in needing to use configural information that makes this effect happen. So I went through this faster than I expected, but so anatomy matters. The log polar network has these nice properties of inversion effects that fall out of the topology of the cortex and the nature of the problem. So fine level discrimination of homogeneous categories versus basic level categorization shows a much smaller effect. They also have these they have this rotation and scale invariance, but again, you lose translation invariance in the original image. But we think that that is not, that, you know, it's more biologically plausible to model humans that fixate on objects at multiple locations. So I want to thank, so we include that using Euclidean coordinates and high resolution everywhere is the wrong prior for models of human and primate vision. I want to thank the following Gurons who worked on this. You know, as we know, the on is the unit in most sciences, like the neutron in physics and the neuron in neuroscience and the person in psychology. So we call Guru members Gurons. So thanks for listening. Any questions?